So I like the title of this seminar, Climate Science Born in Hamburg. And so this is an element, and I would hope that others would also contribute to that. So the overview, so there are two links that you can read about Klaus Hasselmann. And I'll say a few words on his professional career. Then the overarching motive of the blind humans and the elephant, which guided this group of authors to summarize what he has contributed to climate sciences. Then a few words on ocean waves and WAM. And with Klaus in the audience, I'm a little bit hesitant because my knowledge here is rather shaky, so it may not be entirely accurate. Then climate, the paradigm shift of dealing with complexity. Then climate and society, and organizing climate science in Hamburg at the Max-Planck Institute and beyond. So these are two things you can read if you want to read. There's an interview which Dirk Olbers and me did in 2006 with Klaus. It's an extended one, and so it tells quite a bit, I think. And it is also included in the book on the right-hand side, which is the one that Jelka just mentioned, namely From Decoding Turbulence to Unveiling the Fingerprint of Climate Change, the Science of Klaus Hasselmann. And I think in the end, there will be some indication that Klaus won a certain award a while ago. This is done by a larger group of co-workers, friends, and so we cannot have everybody on the cover, but I mean, I would just organize that to a large extent. And this was prepared on the occasion of his 90th birthday, 3 months ago. And when we prepared that, we had a hunch that he may get this award, but of course we didn't know that. And also it was not written for the Nobel Prize winner, but it was written for the scientist Klaus, who turned 90 and had so much importance for many people's work. Now, the curriculum vitae. So he was born in 1931 in Hamburg. And because of the political conditions in Germany, his family went to England, emigrated to England, and of course took the young Klaus with them. So he went to school in England from 1936 to 1949. And every now and then he also claims to be actually an Englishman. And I think he's still counting in English. And in July 49, so about 1 month before I was born, he took his final high school exam and returned in August to Hamburg with family. Of course, Hamburg looked rather different at those times. And then, quite remarkably, he took a practical course in mechanical engineering at the company Mencken Hamburg in Hamburg for half a year, before he went to study physics and mathematics at the University in Hamburg, which ended with his diploma examination by Professor Wiechhardt, and that was a thesis on turbulence. And after that, he went to Göttingen, where he studied physics and fluid dynamics at the university and at the Max-Planck Institute for Fluid Dynamics. He got his PhD in 1957 with Professor Tolmin, and then he became research assistant to Professor Wiechhardt at the Institut für Schiffbau at the University of Hamburg. 61 to 64, he was assistant and then associate professor at the Institute for Geophysics and Planetary Physics. And he was also at the Scripps Institution of Oceanography. No, he went from Hamburg to Scripps in La Jolla, California, got his habilitation in Hamburg in 1963. Then back to Hamburg, lecturer at the university, professor at the university, but in between he left for half a year to go to Cambridge, and later become 96 department director and professor at the University of Hamburg, and he went away for 2 years to work in Woods Hole. I think at that time, first time our We met indirectly, at least. I got a contract with the Sonderforschungsbereich in those days as a programmer, and I think Klaus was the speaker of the Sonderforschungsbereich, and he signed my contract. Of course, I didn't know who he was. Then again, until 1975, a professor in geophysics in Hamburg, and then the big change in February 75 to November 99, he became director of the Max-Planck Institute of Meteorology, or to address the function of a director of a Max-Planck Institute properly, the director got an institute, because in normal institutes, it's so that the institute is getting a director, but in case of Max-Planck, it's the opposite. It is so that the director is getting the institute, which he can or she can form in the way he or she wants to, at least to a large extent. Later, in the beginning of 1988, he also was director of the German Climate Computer Center from Deutschen Klimazentrum. In 1999, he retired, and then the big event was in October 2021 when he got the Nobel Prize in Physics. Then we also have a list of awards here, and I noticed it's incomplete. And so what can I say? But the most important likely are here. So it began in 1963, and then one after another award finally arrived, and this culminated in the Nobel Prize in Physics in 2021. So on the left side, you see this gentleman. He seems to be in a upbeat mood. And actually, he has his medal there in his hand. And on the right-hand side, you see him in a discussion we had in my working place in Hamburg with a journalist. So that's the way he looks in these days. And now we come to this, to the elephant and the blind people. When we started to write this, to compile this book, we noticed that the spectrum of issues Klaus was involved in was actually much broader than most of us had noticed. And so some of us knew, say, the ocean wave part very well, but they didn't know, say, what he did in climate and society. And so we all had a good understanding of individual parts, and we have here seven issues: ocean waves, matrons, that nobody understands a part of him. Maybe he just understands it himself. Stochastic climate model, reducing phase space, remote sensing, modeling strategy, and climate and society. And we tried together to build a more complete understanding of what he has done. But we were the blind people, and Klaus was the generous person who endured us trying to find out what is happening with his ear or his teeth. And so, number one, ocean waves, and I hope that I'm not talking too much nonsense now, is one of these topics, and it is the first topic he worked with, and we started in the 1960s. And his first important paper were Grundgleichungen for ocean wave spectra. And so he just came out of that, and I'm not sure, I think it was quite a change to what otherwise was discussed in this topic. And experimentally, he derived, of course not alone, but in a big field experiment, the Ion-swap spectra. And here I have one diagram, and I'm not sure if I interpreted it good enough, but this was measured off the island of Sylt, and it shows how waves developed when it were along a certain down the wind. And we see that we first had, that is a red curve, we have relatively low waves with a high frequency, but these low waves change under the, while traveling along, and become higher and higher, but also shorter, longer, the period becomes longer. And the immediate outcome of this was, not the immediate, one outcome was that these were both, Klaus and his wife, Susanne, were instrumental in getting the third generation model VAM running. And this was combined with the assimilation of satellite data, and there's now an operational system running at ECMWF. On the left-hand side, you see a book which was compiled by a larger group of authors, and the editor, the main editor, I think was Hermann Kohlmann. So that was a big achievement. And we at Heraeon, we still run this model, and it's also running in very many different places in the world. Somebody said, if there would be a Nobel Prize for oceanography, then this achievement certainly would also should result in a Nobel Prize for Klaus, but not only him, but also his wife. And so we have on the left-hand side an ocean spectrum, and the way they usually present it, this is given as frequency direction spectrum. And the direction is given by the angles, I mean, in which way these waves travel, and the distance from the center denotes frequency. This actually is from measurements taken, aerial measurements taken with a nautical radar system, VAMOS, in the South Atlantic, and we essentially see swell with a period of about 11 seconds traveling towards the southwest. So this is a typical diagram of that. And if we come to the Grundgleichung of the dynamics of ocean wave spectra, then we have the wave action density as a prognostic variable, which is proportional to wave energy per frequency. And it has 4 coordinates, namely the 2 spatial coordinates plus the components of the wave number in both directions. And then what we see here is the usual, on the left-hand side, the usual change of this property, and this is balanced by input variables. So there's the input from the atmosphere, the dissipation, and this was, I understand, a major achievement of the Hasselmanns, the nonlinear wave transfer. And the sketch is described, is shown below. And here we can see that this process is actually leading to the shift of the peak in the spectrum towards slower and higher waves. And if you want to read more about that and you don't want to go to the original book, then you can read this wonderful book by Ralf Weisse, where I had the honor to act as a co-author, which is available through Springer Praxis books. So that was the part on the waves. But maybe more important or more visible was the issue of climate. Well, so what was known at the dawn of modern climate research, we have a diagram here from Mitchell, 1976, which shows variance on all time scales, but a number of peaks. Of course, there's a spike in 1 year and 1 day, these are deterministic cycles, but also broad peaks, and we have never 0 ones. So it is a continuum of variance we have here. And so what happened in 1970, what did I say, 5? No, likely it happened a little earlier, that Reimer Lust, that's the gentleman on the left-hand side, who sadly passed away last year, then president of the Max-Planck Society, asked Klaus Hasselmann to build a Max-Planck Institute to study climate change. Klaus and me, we made an extensive interview with Reimer Lust, and I think it's an interesting document of how times were. And a major outcome of this, immediate major outcome, was the stochastic climate model. And here we see the impact of this model, namely how do you call it? Anyway, this document of the Nobel Society, and here we see the cover of this article, which was rather complicated. But I mean, if you come up with something new, then it's maybe no wonder that it's in the beginning rather really complicated, and then boils down more and more to simple things when people get used to it. And so I summarized that in our stochastic climate statistics of, I forgot what the title of our book was. So essentially, you can, if you shorten it very much, then you say, let's think we have a dynamical differential equation, like the time derivative of x is given by d, x, and f, and we have a force in F and dynamics d, and let us assume that x is made up of two components, and that's the key point here, y and z, and y fluctuates on long time scales and z on small time scales. So if we have that and linearize, then we find for the slope component, that is y, that the time derivative is something like a constant times y plus w, and d is less than 0 as x is, as y is stationary, so there should be 1. The effect w of the short-term variable z on the long-term variable is considered to be stationary and have no noteworthy autocorrelation because it's short-term. So it's considered noise, or it's named noise. After the discretization, we arrive then at something rather simple, namely that the state at time t plus 1, and it should be a lowercase y, is equal to alpha yt plus ywt, with w being Gaussian. If Gaussian, w is Gaussian, then y is governed by an autoaggressive process which has a red spectrum. I mean, this is the strongest simplification. And the trick is, or the significance is seen on the right-hand side. Here you see two spectra with different alphas. And the lower curve is alpha equal 0.3. So we have yt plus 1 remembers only a little of yt, and it has and this short-term variability is on the right-hand side, and or the noise, the forcing noise, and we have more variability on long time scales. So this is typical for red spectra. But if alpha is 0.9, then we have the other diagram. So it is much higher. So this is essentially it. Namely, if you run a system, a linear system, with memory and force it with white noise, then you get a red spectrum. So this system transforms the white spectrum to a red spectrum. This sounds rather simple, and nowadays it is simple, but it wasn't at that time. So these models of the dynamics and of the components of the climate system generate variability on all time scales without being provoked for doing so. And in other words, we have smoke without fire. And if we look at these three diagrams, this shows, it was published in the early 1980s, and we had not much data then. On the right-hand side, the mean 500 hectopascal geopotential height field, and the other two are the maps. It's just for January, I think, yeah, for two specific years. And now you could, of course, ask, if you look at these, why is 1981 so different from the time mean? And what's the difference between 1981 and 71? And the answer is none. It is part of these random variations we have in the system. There's no, at least we didn't detect it so far, a signal in these differences. And we must be aware that if we look at things, changing conditions, that it may be due to noise or to unprovoked variability. Here I have another diagram, which is with much longer timescales from Schulz and Mudelsee, and it shows on top oxygen isotope time series from Greenland GISP 2 between 15 and 16,000 years before present. And on the bottom, you see the spectrum. This has now a different, it's no longer logarithmic, presented as before. And you see it fits very nicely, the top diagram, even though it's not fully stationary, the top diagram fits very nicely that of a red spectrum. Now, before this concept was introduced, and again more and more so in recent times, people were convinced that all remarkable developments in climate must be related to one or more external drivers. But Klaus Hasselmann demonstrated that there's smoke without fire in climate variability. Low frequency variability is generated as the integrated response to short-term fluctuations, as for instance, macro-turbulent atmospheric flow at mid-latitudes, which would be the short-term fluctuations. So in that sense, the storms, our conventional storms, represent for longer time scales noise. And that's a significance. A new task for climate science, climate analysis emerged, namely the identification of a small space within which the dynamics of this considered signal rules, while the remainder acts in the spirit of the stochastic climate model as a stochastic forcing. And this is, in my understanding, the pips and pops concept. I'll come to that in a second. Thus, changes are a result of both external and internal stochastic forcing. And the question arises if an anomaly is just internally generated low frequency variability or caused in part by specific external causes. And that is the detection and attribution question. Now, this is another paper, Pips and Pops, a reduction of complex dynamical systems using principal interaction patterns, interaction and oscillation patterns. Again, I should say that the paper is very complicated and it's a hard read. But this is just expressing that or illustrating that this was reading something new. And in my understanding, this was a paradigm shifting achievement, which got him the Nobel Prize. Of course, I'm not sure if the Nobel Committee understood that. But for me, this is the key achievement. Now let's talk about this a little, and I have some sketches here. So if we have the full system, then we have, that's what is within the blue line. And we have lots of processes, smaller and larger, and what small and large means, I don't know. And there are a number of external influences on the system, and we want to analyze that. And so what we do is we determine something what we would call a signal space. So we select a subspace of these. This depends on which problem we are looking at and may be guided by the best predictability. Only part of spatial and temporal scales are selected, and also the parameter range is limited. So instead of the full system, we have this reduced system, and that is the PIP, Principal Interaction Pattern System. And when we also reduce, of course, the number of external influences. And the trick is that the effect of all the processes we have not included are taken care of by conditional stochastic models. In the case of the stochastic climate model, for instance, there's no conditioning. So that's more or less absolute, but this is just a matter of the concrete case. So the trick is to find a small subset of processes, and the rest is considered so to speak, a bathtub of stochasticity. If you're looking here carefully, then you would say, hey, this is the same what we are used to do when we look at parameterizations in climate models. That's indeed true. The diagrams I'm showing here, I had originally designed for parameterizations, but it fits exactly here as well. So the PIP system is small, takes into account all processes which are really significant for the considered dynamics, and parameterizes the effect of all other processes. And the skill may be examined by checking the PIP model's ability to do predictions of the considered dynamics in the full space. This is what I call the reduction of the phase space. And I suggest this was a paradigm shift. We have many examples for the linear variant, the POPs, on ENSO, the Madden-Julian oscillation, the life cycle on baroclinic storms, for instance. But we have no good examples of low-dimensional nonlinear dynamics, such as the Lorentz system, at least so far. So one could think, and I'm sure that Klaus had the idea, that it would be possible to isolate something like the Lorentz system in the full dynamics. But so far, at least I'm not aware of successful cases. And young, promising scientists may be able to provide these examples. An almost trivial example is the stochastic climate model. In this case, we have only a one-dimensional system, and we have the noise is not conditional. But the concept of detection of non-natural climate change and attribution of likely causes of such change may be understood in this framework. And I'm convinced that when Klaus designed the detection attribution part, he had all this in mind, but he was not very explicit about it. And so he published the Pips and Pops paper years later, and it eventually came out in 1988. And the structure of quasi-realistic dynamical climate models with the signal space defined by space timescales and with activating the effects of non-resolved scales by parameterizations may also be seen in this concept, even though that was already in use. But when I came into this business in about 1971, no, not once, 76, people could not really well explain to me what a parameterization is. They just said, we make an ansatz. In the detection attribution, that is a key result in the contemporary climate change concept of the reality of anthropogenic climate change and the possibility to steer it by a political action. I mean, when you say first there is something related to external drivers, and this external driver is to a large extent the presence of greenhouse gases in the atmosphere, then of course, when we accept that we can steer how much greenhouse gases are in the atmosphere, then we can also steer to some extent at least the amount of climate change. Now let's go briefly to the detection attribution part. And this is the main achievement of Klaus Hasselmann. I personally think it's more like a corollary of the Pips and Pops, but okay, it doesn't matter. So the detection and attribution of climate change has two steps. And first, we prove that recent change, and we are talking about observed changes. This is not a model product. We try to prove that recent changes inconsistent with the hypothesis of natural or internal origins. That is, we do a statistical test and we reject the null hypothesis. So this is a statistical proof. And this is illustrated in the top right diagram from this 1970, whatever, 7 paper. And here you see 20-year trends of not really global mean temperature, but of a spatial subset with good data coverage. And the solid line is what we derived from observations. And the dashed one is what we derived from a model simulation. So the key part is, of course, the dashed one. And then you see we have symmetric band around the zero. And these are estimates of the natural variability, and the sources are given below. And what you see here is this, the critical variable, the intensity of 20-year trends varies between these, mostly within this range of natural variability, but beginning in the, I mean, this is a 20-year trend, so I'm not sure what the last value is. Anyway, likely 1987. In the last few years, we see that the state leaves this band, and that means the development can no longer be explained only by internal variabilities. There must be something external. It doesn't say what. It only said there is something. And to illustrate the concept, we applied it also to the output of a climate change model run, and that's a dashed curve. And we see it's not identical, of course not, because there's internal variability in the system, but we see fundamentally the same behavior. The second point is that we demonstrate that this recent change, which we have detected as needing an explanation, is consistent with specific forcings. And this is no longer a statistical test, but the plausibility argument. So it could be that they are, we can just say it could be explained this way. This is not proof that we cannot explain it with others. We can, of course, check which the other processes we can really deal with, the other drivers we can deal with, but there may be others we are not aware of at this time. And this is the right-hand diagram in the bottom, which shows us the trajectory of, in this case, I think it's, I'm not sure, it's 50-year temperature trends from the beginning of instrumental data until the last 50-year interval, which we had at the time. And you see it started that all variations could be explained entirely by solar variations. And we could also have here something for natural variability. And then it developed slowly, blah, blah, blah. And so in the end, we can see we need to explain this. We cannot do it only with CO2, but we need CO2 plus aerosols. And of course, it would be fun to extend this curve, but so far, this has not happened, and maybe better diagrams are available now. So this is, on the left-hand side, you see also the papers which Klaus wrote on these topics. So he started with a paper on the signal-to-noise problem in atmospheric response studies. And this was first applied to the effect of El Nino and things of that sort. 1979, again, a very complicated paper. But in 93, then he came up with optimal fingerprints for the detection of time-dependent climate change, which was a wonderfully clear paper. So it was just a really well-written book, text, while the first one was essentially giving the science. And you could see how he struggled with this topic and came to a solution. Then the third one was the first paper which came out on actually doing it. And then there are two more generalizing all this. So much on that. So we come now to the climate and society. And so then after the detection attribution effort had been successfully done in 96, in later years, then of course the question came up what to do, how to steer. And Klaus came up with his global environment society and society model, abbreviated GES. This was also published, one of the papers was published in 1907. And this is illustrated with this diagram here. So what you see is you have four boxes. And on the left-hand side, you have global and regional socioeconomic models or systems. And these systems generate greenhouse gases. They generate emissions of all kind, deforestation, pollution, whatever. And this affects climate, which is described in global change models. These models, these systems change their characteristics, and the models describe that, in which feeds back into the economic system via climate change. Now, if we want to steer that, then we first need to know what we want. So what do we consider a good state? And that's maximizing global welfare. And here society comes in Klaus Hasselmann's concept on the stage, namely to decide what is the global welfare, human welfare function. But otherwise, we don't need society. Once this decision has been made, the rest is done by science. And then we have to determine what are the costs to adapt, to live with these climate changes. And we have to determine the costs which are incurred to avoid these. So we have two types of costs, and then we determine that mix of instruments which give the least sum of costs, abatement, and adaptation. So this is an optimization problem. And so I allow myself here to come up with some critique, namely, this is something what I did with my sociological colleague Nitro Steer. And we claim that society assesses the situation not by own objective experience, but by reporting and judgment by experts, media, and conditioned by cultural preferences. And so here we have again the four blocks, but between the two blocks on the right-hand side and the two on the left-hand side, there's something in between. So we have those who interpret what happens in the climate system, And what they interpret is given into the social construction system of society, what society thinks it makes sense. And this all leads to a certain change of the real situation. And it's not the costs of abatement and adaptation, but it's the costs of perceived adaptation and abatement. And I notice that I have here cost instead of costs. So this would be a very different thing. And so we claim that societal decisions are based less on scientific constructions, but mostly on social constructions. And we also said that a global, not we, that others said that maybe it would be difficult to define a global welfare function. And indeed, I think it cannot be determined. So if you look at the Millennium Goals of the United Nations, what are the most critical challenges of humankind? Then we have 16 different topics. And I would presume that in many cases, other topics will be considered dominant and not necessarily climate, which is certainly the dominant publicly discussed challenge in the West. Anyway, now we come to the last point, organizing the climate science in Hamburg at the MPI. And here I'm just using transparencies which Klaus Hasselmann presented at his Steinhausen Vortrag in 2006, and this is in German now. And I thought it would be a pity to translate anything here. So he said we had 3 phases, and I forgot what the third one is because I took it out for some reason. I'm not sure why that was so. So the first one from when the institute started until 1987, I guess that's the time when the DKZ came up. That was the Aufbauphase, the phase when MPI was built. And actually from zero to a world-leading institution. In 1988, then it was expanded. In this time, Klaus was the director. There was a third phase, I forgot what it was, but he was no longer director. So, and the strategy of the first phase was to test the concept of stochastic climate model using simplified climate models, and at the same time building a realistic coupled ocean atmosphere carbon cycle model. And the idea was after such a realistic climate model is available, actually I call them quasi-realistic climate models, then one would apply the stochastic climate model to analyze the natural climate variability. And this was realized by Ernst Mayr-Reimer and Uwe Mikolajewicz, who worked about natural variability of the ocean circulation induced by atmospheric variability. But as he said here, danach MPI abgelenkt durch andere Entwicklungen. So it went in a somewhat different direction, and this was less important. And then we had a number of future developments. So first of all, we expanded the Hamburg climate model ECAM LSG, large scale geostrophic, to an internationally leading climate model. And that was done in particular after the advent of Lennart Bengtsson, the co-director, Erich Röckner, Mayr-Reimer. Then the Institute got, the system was expanded by having atmospheric and oceanic chemi and tracer modeling, again done by Röckner, Mayr-Reimer, Martin Heimann, in cooperation with Kotzen. Mujib Latif was leading in improving the El Nino predictions, and also the issue of stratosphere, atmosphere, and volcanism, effect of volcanism got some attention, led by Graf and Oberhuses and others. A pretty important part was that the Institute got involved in scenario calculations for the IPCC, and here the name of Kubash has to be given. Then the detection attribution part and coupled climate socioeconomic models. The modeling strategy, so first was to building a fast ocean model. I mean, so that you can really do long integrations. That's the LSG with Ernst Mayr-Reimer. And then came the cooperation with the theoretical metrology at the university in the import of the ECMWF atmospheric model. That was a Fischer group, and in particular Erich Röckner. And this group is nowadays the Nejelka-Zadar group. So I find it quite nice that I have an opportunity to speak about all this in the theoretical metrology of the University of Hamburg. I mean, this is all described in the various interviews, but what happened then was, and that was in the early 80s, that Erich Röckner had his own atmospheric general circulation model. Actually, it was only hemispheric. And so he was persuaded to give his own model up and to use instead the ECMWF model, and by adding the parameterizations of Erich Röckner's system. And he was smart enough to say, okay, this model was my baby, but this is a much better chance. And so he gave up his own model and took another one. And I think that was quite an achievement. It was really instrumental for all this going on. And so then the Deutsches Klimazentrum was set up in 1988, and Leonard Bengtson became co-director of the Max-Planck Institute, and you see him on the left-hand side. I'm not quite sure when that actually was. It must have been in the first part of the 1990s. And then the model system was expanded to become the Earth System Model MPI-ESM. The top right saying you see the original coupled system, where you see essentially the atmosphere and ocean and land surface properties and the cryosphere. And then later in the MPI-ESM model, you see also that the carbon cycle is added. And now all this was only possible because the computer system was regularly improved. So this all started in 1985. Before that, there was already a computer by the institute. But in 1985, first real big computer was there. We controlled data Cyber 205. I mean, this is also told in the interview with Klaus Hasselmann, that everybody expected him, after he set up the institute, to immediately buy a new and big computer, but he didn't, because he said, I first want to study how the system works, and then when we've done that, then we can build, can go to a big computer system. And so they said only one processor, and had 2.5 gigabyte, what is that, Festplattensystem. So less than my Apple nowadays. In 1988, already the next one came, Cray, with 4 processors. 6 years later, Cray, 16 processors, and now 10 terabyte, 128 gigabyte. 2002, 2009, that was after Klaus's time. In 2015-16, the Mistral, which is, I understand, is just phased out. And if you look at this, the development in time, then you see a red curve, the most advanced computer in the world, measured in terms of gigaflops per second. And so the dash curve is the DKRZ system, which was never number 1, but had honorable rankings such as number 28 in 2010, or in 94 in 1994. And so it usually was it was among the first 500, but not always. But the Ministry for Science and Technology regularly pushed money into the system, and these were substantial numbers. Now this brings me to an end. So what I tried to do was to bring you closer to this elephant. That this was really quite a spectrum of achievements, quite different. I mean, the ocean wave part was done by, he did with very different people than the climate part. The metrons he did mostly with his wife. Climate and society, he did also with other people, remote sensing as well. So we were really, we who had the honor and pleasure to work with him, we were just getting learned about a special aspect of his work, but never the full spectrum. And this is ending this. So on the one of them is Klaus Hasselmann. I'm not sure if you recognize him because the younger one, the younger looking one is Klaus, and the older one is looking is me. So this ends my presentation.